a recursive problem is when you're using, or a recursive formula is when you're using past values to determine the current integer you're looking for. So instead of just plugging into an equation x equals 3 into the explicit formula to find the value for the output for when x equals 3, you would instead be finding x equals 2 and then using x equals 2 to find out what x equals 3 is. And so here's a couple of things to note about reoccurrence relations. So in order to find the reoccurrence formula, you number one have to assume that your base value is correct. So as mentioned before in this example, if you're trying to find x equals 3, you have to assume that the value you have for x equals 2 is correct, because that is your base value and that's what you're starting with. And then number two, you have to assume that there's a value for n minus 1 if you're looking for the value of n. And the logic for this is similar to the logic of dominoes. So as you have domino 1 that knocks over, we know that domino 2 also falls over. So in the same way that we know that there is an n minus 1, then there has to be an n. So for the sake of reoccurrence relations and trying to find this formula, we assume that n minus 1 exists, and therefore n has to exist because n minus 1 exists. And so kind of moving on to talking about the game, the Tower of Hanoi is based off of an Indian legend that states that after 64 golden discs are stacked up, the world would come to an end. And we're going to talk a little bit more about this formula you see right here. But when you plug it into the formula, you get 1.8 times 10 to the 19th seconds, which is estimated to be around 584 billion years, which some scientists estimate to be the life of the universe. The life of the universe. And I got this from the textbook, so I just think it's something to be noted that number correlates. And as for rules of the game, so the game was developed by Edward Lucas, who, according to his rules, only one disc can be moved at a time. Only the top disc of one stack can be transferred to the rod of another stack or an empty rod, and larger discs cannot be stacked over smaller ones. So let's take a look at the game. So my goal is to get all of these in the same order on this rod. But I have to follow these rules. So I'm just going to start by moving this one over here. So that's one move. And then this is my second move. So that's 2 moves, 3 moves, 4 moves, 5 moves, 6 moves, and 7 moves. And so with those 7 moves, I got this stack over here to come over here. And so there's a little bit of logic behind this. So there's a little bit of a pattern to be noticed even after we add more cakes onto the stack. So what we want to do is we want to have the value of k minus 1 or n minus 1, however many you have in your stack, and you want to have that value ended up here as you make that final transfer over to get to that endpoint. And that's just one thing to note, that's like a constant that'll stay even as you have k to 4 or 5 or 6. Right before you are able to transfer that base over, you have k minus 1 stacked up in the middle. And so then this leads us to the formula that we saw before. And so this is the recursive formula as seen, where m is the amount of moves that it would take minimum for you to solve this puzzle. And so as we saw for and where k is the number of discs, so as we saw for the number of 3 discs, we had 7 moves, right? So using this, we can find the amount of moves it would take for even 4 or 5 of those cakes, as we can plug in the value for 5 or 6. For 4 or 5. So for instance, if we want to go up 1, right? Say m of 4, right? So if m of 4 went over here, then we have m of 3, which is a value we have, which is 7, plus 1, plus 7, which is 15. And then we would have the value for m of 4. And then using that value for m of 4, we can find m of 5. And so that's kind of how recursive formulas work, where they take that past value, our base value, and we kind of replug it in. Our version includes 4 poles with 2 different colors, each with the same amount of cakes, which we're going to call variable n. Now we want to stack the poles so they have the same color. So we're going to have 2 different colors on the poles, one pink, one blue. The in-person one's going to look a bit different than the one I'm going to use online. For the sake of demonstration purposes, I'm just going to use Google Slides to demonstrate the game. And one of the rules for this game is that for our variation is that cakes of the same size cannot be stacked on top of each other. what we're going to have to start with our base assumption is what we got in the first trial, in which we had 3 of the cakes, and we used 14 moves. So 14 total moves is our base assumption for A of 3. And then as we go on to A of 4, what I did was I put 1/2 of the previous base assumption, and then I added that on to 8 because we had 2 towers, so we weren't exactly using 14 moves for the whole entire tower, but much rather we were using 7 moves per one of the colored towers. And so doing that, adding the extra moves plus that 0.5 of that again, we can find ace of 4. And same thing with ace of 5, except it's plus 16, and then ace of 6 is with plus 32. And so what I noticed was an increase by 8, and I thought this would be helpful when it came up to formulating our recursive formula, and in which I got for my equation 0.5 a of n minus 1 plus 16 n minus 3. And I think that this is interesting to note because this version of the towers mimics the original, in which it's almost as if we doubled it. And so it is interesting to look at how the formula has doubled for the towers we did, the altered version we did, in comparison to the original. Presentation. Thank you so much, and I hope you all enjoyed.